Okay, so let's see what we've got here in our table. All right, now again, we talked about our two different situations here, right? We reviewed a linear function here, right? And we said that linear functions have a common difference, right? Linear functions and arithmetic sequences, they're like very closely related to one another. Linear functions are continuous, so a difference would be linear functions are continuous, right? You can plug any value into a linear function, whereas arithmetic sequence, right, is discrete, right? You have this like certain points in the pattern there that you get. But they both have in common a common difference, right? And they have a constant rate of change. Exponential functions, those are like our geometric sequences. Similar kind of difference, though. Exponential functions, they are continuous, right? So we can like put in a whole interval of x values, whereas geometric are just discrete, right? We have point for the pattern, and then the next step in the pattern, and the next step in the pattern kind of thing. But they do have that common ratio that we can use, okay? And that means their rate of change is changing. It varies, okay? So for Cedar Grove, right, we started with 30,000, and we had a 6% increase every year. And then Maple Grove, they different situation. We started higher, but we added $1,200 every year, flat, just $1,200, okay? And we're comparing these two job offers by completing this table. So you look here at the table, and here's what your table should look like, okay? Something like that, okay, with rounding and stuff like that. All right, so Cedar Grove models what type of function? Is it exponential or is it linear for Cedar Grove? Exponential. Okay, because it has a common what? Ratio of what? What are we multiplying by every time? 1.06. Okay. So the R that we talk about when we talk about like exponential functions and the R for common ratio are actually two different R's. The common ratio R is actually more like the B. It's very confusing, but that's what it is. Okay. Yeah, I agree though. That is confusing. Okay. So. And then we use R in the other one because it's for the rate, right? Because it's the percent rate of change. Anyway, all right. Maple Grove models what type of function? Linear or exponential? Linear, because it has a common what? Difference. Okay, it's a constant rate of change. Common difference of what? What's the difference every time? 1,200, right? We're adding that flat rate. Okay, now, letter C. If you plan on moving to a different state in 5 years, which company would be the better option for you to choose? Okay, why Maple Grove? So you get more in 5 years. What do you mean by you get more? Like what do you mean by that? Amount of money? So like how are you comparing them? What are you looking at? So are you looking here, for example, and saying at the end of 5 years I'm making this at Maple Grove, and at the end of 5 years I'm making this at Cedar Grove? Okay, and the difference then, and you're saying Maple Grove you're making more. Okay, so Maple Grove. Okay, because we make more money. Okay, each year than Cedar Grove. Okay? Maple Grove, we would plan to work there because we would make more money than Cedar Grove every year. Every year we're making more money than Cedar Grove, right? Well, sorry, every year for those 5 years, I should say. You're right there, Trey, yes. All right, now, letter D. If your plans change and you don't move, which company would be the better option to choose as a long-term career? Hannah T.
I said Cedar Grove because if you look at like the 14 years, you already make a lot more than you make over $10,000 more.
Okay, Hannah T says Cedar Grove because by the end, right, and not even by the end, right, we start making more money at Cedar Grove by year 11, looks like, right? By year 11, we start making more money, okay? So after year 11, we're making more money per year, okay? So Hannah T says Cedar Grove because after year 11, you're making more money. Shh. Did everyone else say Cedar Grove?
Yes.
Yeah. Okay. No one said Maple Grove? So let me show you something here, all right, which maybe you didn't think of. So I hear what you're saying, Cedar Grove, Okay, and I think that's what the worksheet is probably wanting us to say here is Cedar Grove. Okay, if I had to guess, because we're looking at just how much we make every year. Okay, because after 11 years or more, okay, we will make more money there each year. Okay, so after the 11th year, right, we're going to make more money at Cedar Grove than we do at Maple Grove. But, I was doing this problem ahead of time, and I was like, you know what? But think about this, though. If you worked there for 14 years, that means you made this much in the year before. That means you made this much in the year before. You made this much in the year before. So when you work 14 years, yes, that's what you make in your 14th year, but the overall amount of money that you make would be if you add all these together, right? Now, if we add all this column up, the sum is $630,451.95. Okay? If we add up this column, guess what? $669,200. So, it's not so clear now where we should work. Yeah, Chloe?
I mean, if you're thinking realistically, Maple Grove is probably better because a lot of people are less likely to stay at one job.
So that's a consideration too, right? You got to think about whether you're going to be staying there for long term, or you're going to be staying there short term or not. Exactly right. Okay, that's another big deal, right? And you can see here that yes, even though you do start making more money at Cedar Grove eventually, overall, even after 14 years, right? So we started year 11 is when you start making more money at Cedar Grove. But overall, even 3 years later, at year 14, you still have made more by going to Maple Grove first than at Cedar Grove. Now, will these two always be like this? Will Cedar Grove always be less than Maple Grove? No. Okay. So over the years, that sum's going to get closer and closer and closer. But even here, where you are making less money than at Cedar Grove, okay, so like if you had a friend that was working at Cedar Grove and you work at Maple Grove, you overall would still have more money than your friend because you started out higher and it took it longer for it to catch up. So these are things to think about, okay? These are things to think about here, okay? So.
It's like you're considering teaching in Montgomery County or Fred.
That's true. Or when you miss a raise, for example, for 1 year. If you're supposed to get a raise or something like that, you don't get that raise doesn't hurt you just for that year. That raise hurts you for the rest of your career, right? If you're supposed to get like $1,000 raise 1 year, right? Yeah, you missed that $1,000 for that year, but then you missed $1,000 the next year when you would have had it, and the year after that when you would have had it, and so on and so forth, right? So it hurts for a long time, not just for that one time that you miss it. So anyway, something to consider there. Okay, and something you should consider, when thinking about a job and stuff like that too. Okay, you got to think long term in addition to the short term. Okay, all right, let's flip it over here and let's take a look at some more examples of linear versus exponential. Okay, so in letter A, okay, what type of model would be used for each situation? Linear, exponential, or neither. Now this is weird, I know, because for those of you that had Ms. Sliger, right, the three options were linear, quadratic, or exponential, right? Well, for us, we're going to talk about just linear, exponential, or neither for right now. If you had me, we also did linear, quadratic, exponential, but we're just going to do linear, exponential for right now. Okay, letter A. A savings account that starts with $5,000 and receives a deposit of $825 per month. Is that linear, exponential, or neither here? Linear? Why? What makes it linear? You're just guessing. Okay, that's fine. You can guess, but Jackson?
It goes up the same amount every month.
There you go. Perfect, Jackson. It goes up. I couldn't say it better myself. It goes up the same amount every month. Okay? Constant rate of change. You were right. But I want you to be able to defend it too if you need to. Okay? Constant rate of change. Letter B. The value of a house that starts at $150,000 and increases by 1.5% per year. That's going to be exponential. Yeah, we're going to be multiplying by the same. We're multiplying a common ratio here, okay? So, multiplying by common ratio, you could say there. And we don't have to defend all of these here. 1.015. right? Because that 1.5% is 0.015 as a decimal, add that to 1. So anyway, okay. We don't have to defend all these. I just want to do it for you there. Letter C, Tina owns 4 rabbits. She expects them to double each year. Linear or exponential or neither? Doubling every year. We're multiplying by 2 every year. Oh, I hear what you're saying. Okay. I see what you're saying. So neither, I'll put neither / exponential, because you're right. We can't guarantee that the rabbits will actually do that, but okay, I hear what you're saying. Okay. I think they're shooting for exponential, but we'll take neither too. All right, letter D. The cost of operating Jelly's Donuts is $1,600 per week plus 10 cents to make each donut. Is that linear, exponential, or neither? I would say linear because it's like a regular amount, 10 cents more per donut. So I'd say linear there. But it does have the week rate in there too. I hear what you're saying. Yeah, it'd be like linear. I'm not sure, but I think we can be okay with saying linear there because I think we'll just maybe focus on per week. Maybe it's a linear relationship each week. So each week, I'll say that. We'll say it's linear for each week. Okay. The value of John's car that depreciates 20% per year. Depreciating 20% per year. Is that linear, exponential, or neither? Exponential. Okay, yeah, it's again that 20% loss, right? So that 20%, that's changing, right? You lose 20%, if it's $100, you lose 20%, now you're down to $80. But then you're going to lose 20% of $80 after that, and so on and so forth, right? It's like the amount that you're changing is different. All right, and letter F, the height of a ball that is thrown in the air. Neither. Very good. And in fact, can anyone, it would be a quadratic relationship. Remember, we've talked about like the flight of objects through the air and stuff like that, and typically we use quadratic to model that. All right? All right, number 3, one of these situations here, which situation could be modeled with an exponential function? So again, I'll read them all out, and then we'll pick one here, right? So number 1, the amount of money in Susie's piggy bank which she adds $10 to each week. Number 2, the amount of money in a certificate of deposit that gets 4% interest every year. Number 3, the amount of money in a savings account where $150 is deducted every month. Or number 4, the amount of money in Jacqueline's wallet which increases and decreases by a different amount each week. Okay, so, Chloe?
2.
Yeah, number 2. Okay, that 4% interest each year, that is going to be your exponential function. Number 1 would be what? Adding $10 each week? Linear, right? Number 3, $150 deducted every month. Linear. And number 4, well, that's nothing, right? Because it's going up and down, and who knows, okay? All right, number 4, which statement below is true about linear functions? Linear functions grow by equal factors over equal intervals? They grow by equal factors over equal intervals? Now, linear functions grow by equal differences over equal intervals? Yes, common difference, right? Common difference, okay? So which statement below? So it's just one of them, so I guess the other 2 must be false, okay? Okay, let's go to our tables and classify them as linear, exponential, or neither, okay? Let's look at our relationship right here, okay? Each hour goes up by 1, and the money goes up by how much? Times 2, times 2, times 2, times 2. So is it linear, exponential, or neither? Exponential. We're multiplying by 2 every time. Okay, times 2. Okay, what about this one right here? Every time our hour goes up by 1, we go from 100 to 200 to 300 to 200 to 100.
That's neither.
Yeah, it's neither. And I wouldn't even say it's quadratic in that case. Although quadratic does have the increase and decrease to it, I don't think you can model that with a quadratic function. Okay, that is a quick and easy way to identify quadratic if you see your function go up and down or down and up, but I don't think this would be actually quadratic. All right, last one, linear, linear, exponential, or neither. Linear, because we are what every time? Plus 150. 150. Yes, go ahead. All right, one more paper here for you. It is almost time to leave. I know, that's why I got to get this out quick. Thank you, Mr. Seaver. Question. A what? I have an ant problem. All right. I'll bring in some of my poison.
I told Grayson to kill him, but he didn't.
Grayson befriended them. Grayson's their king now.
It's like the SpongeBob movie where Plankton controls all the people in Bikini Bottom.
That's right. So what you need to do, Grayson, I need you to command them to return from whence they came.
Oh, it's like a piece of popcorn down there.
What's that, Grayson? You don't want to make them return? You want to hold on to your power?
It's like Simpson with all the Springfield hated him.
They're going to depose you as king. Commit regicide. Still doing okay, Chimera?
Yes.
Okay.
I don't know.
We'll see you after school too. I bet help you out some more there too.
Okay. Is it just you?
No, Miss Watson's there too, and there's like actual tutor, like student tutors too. So, but yeah. Okay. I want to do a few of these problems here. Okay. Yeah, that's what we're going to do. All right, so more exponential free responses. Okay, so this is actually a practice from the benchmark. So we want to make sure we are super comfortable with this. All right. So in 2012, the population of Algeburg, MD, I don't know if that's an actual town. I'm guessing not because it's suspiciously mathematical by name. But it could be because they use Hagerstown down here, and that's a real town because that's where I'm from.
Yeah.
Now you guys are silently judging me from being from Hagerstown. I get it.
North Hagerstown?
North Hagerstown, yeah.
Oh.
Yeah, there you go, Erica. All right. So anyway, in 2013, the population increased to this. So here's the beauty about data, okay? When it comes to data, okay, we don't always get to, it's not always clear what the relationship is, all right? So for example, here in letter A, we're going to assume the population has increased linearly. That means we're going to assume this relationship is linear. But then letter B, we're going to assume that same relationship is exponential. Listen up, guys. So in other words, we're going to come up with two different models to represent this situation, okay, and use it to predict the future. Well, not the future for us, because 2014 is already come and gone, but the future in the situation. So in 2012, okay, right, the population was 9,450 people. And then in 2013, the population was 10,893 people, and we're trying to figure out what the population will be in 2014. Now, if we're going to say this is a linear relationship, okay, what's the rate of change going to be here? Does the rate of change, or is it constant for linear? It's a constant rate of change. So in other words, we have to figure out what's the change in the population from 2012 to 2013. What's this change? How can we figure out the change here? What can we do? Subtract, right? Yeah, do 10,893 minus 9,450. Well, if you subtract them, you're going to get a difference of 1,443. Okay? So if this relationship is linear, how can I predict what the population in 2014 is going to be? Don't need to multiply. Nope. If it's linear, yeah, what are we doing? We need to add the 1,443 one more time. Okay? We're just going to add it one more time. If it's linear, the rate of change should stay the same. And so if we added 1,443 here, we should do it here as well, and we'll get 12,336 people. Okay? That's if we use a linear relationship here. Okay? Because we add the same amount each time. Okay? So again, we just figured out what that difference was, and then we just kept adding. Right now, if it was linear, if I wanted to figure out 2015, I'd add another 1,443. If I wanted to figure out 2016, I'd add another 1,443 and just keep going. Okay, that's one option. Okay, but now letter B says, oh, forget linear. Let's see if it's exponential. Write a function for the population in terms of t, the number of years since 2012, and round your model to the nearest thousand. So we're going to come up with a function now. Okay, we're going to come up with a function now. So let's see here. How can I do that? Well, I've got to figure out y equals, okay, what's my starting amount here? So again, we're going to use a times b to the x, or a t, I guess. We're going to use t for number of years. Okay, so what's my starting amount for this situation? We start at what amount? Yeah, 9,450. Are we told how much it's increasing by every year? What percent? So here?
I don't know, but I divided
Not.
the,
Huh?
I divided the 10,893 by 9,450.
Yeah, that's exactly what we got to do.
1.15.
Okay, 1.15 you said? Is that exactly 1.15?
It was roughly.
Okay, we had to round it. Okay, that's fine, to the T. So yeah, let's just take a real 1 second here, a little sidetrack here, because Hannah did it exactly right, but I want to make sure you guys didn't miss out on it because that's super important. We can come up with this. Okay, if we're going to say this now, this relationship is exponential, okay, that means there's a number we're going to multiply by. Okay, we're going to multiply by something here. We got to figure out what can we multiply by, right? 9,450 times what gives us 10,893, right? That's what we need to figure out, our common ratio here. So we're going to figure that out by just taking 9,450. We'll multiply it by some unknown number, x. Okay, we don't know our common ratio here. I'm just going to say it's x. And we know we're going to end up with then 10,893. Okay? So again, we're saying this relationship is exponential. Exponential means you're multiplying by the same amount each time. To get from here to here, I got to figure out my common ratio. So I'm just going to take 9,450 times the unknown common ratio, and I get this. So divide both sides by what?
9,000.
Exactly, which is what Hannah did. Okay? And we get x is, and this is where Hannah, I think, rounded, right? So 10.
Yeah, it was like 1.15 and then a bunch of numbers.
Okay. 9450. Yeah, so I get like 1.152698413. So we're just going to do 1.15 there because that's what Hannah used. Okay? And so there is that 1.15 right there. That's what we're going to use. There's our equation. Okay? There's our equation. Okay. And so then for letter C, using the model you found in part B, what will the population be in 2015? Now, how are we going to use this to figure out the population in 2015? What should we do here? Yeah, Jackson.
Plug 3 in T.
Wait, plug 3, but the year is 2015, Jackson. Why do I want to plug 3 in for T? That's right. Remember, folks, we started counting at the year 2012. T is the number of years since 2012. So if we want to find the population for 2015, I got to say y equals 9,450 times 1.15 to the third, just like Jackson said. Good job there, Jackson. That's exactly right. Okay, so 9450, parentheses, 1.15 to the third. Okay, see, I typed it in there. Hit enter. 14,372.27. Ooh, what should I round to here, actually? Because we're talking about people, right? So, Sky? It does. Ooh, thank you, Sky. Directions are crucial to read and follow. So, nearest whole number. Thank you, Sky. 372 people. Right. Yes. What happened to the other part of the person? Well, a person is a person, no matter how much of them there is. They're still a person. Okay, even you're missing a finger. That's right. Still a person.
Just a finger.
Just a finger? Still a person. Okay. I guess you could miss so much of that person that they're no longer alive, in which case I guess they wouldn't be a person anymore.
Well, they have person traits. Oh.
All right, last one. The population of Hagerstown, Maryland can be modeled by the function h of t equals 40,518 times 0.99 to the t in terms of time, t, and years since 2012. Now, you'll notice here, explain what the value 0.99 means in the context of the problem. What is 0.99 telling us about the population of Hagerstown? Jackson? How much it's growing every year, but maybe more accurately, how much it is shrinking every year. How do you know it's shrinking here? You're right, because growing can mean either way. You're right. How much is it shrinking by every year?
Well, no one likes the numbers. They just sound outlets.
99 is what we're multiplying by, but by what percent are we shrinking every year? 1%. Remember that for the b value, it's 1 minus r for a decay. And if your b value is 0.99, okay, if you solve here, subtract 1 from both sides, you get negative 0.01 equals negative r, so it means r is 0.01. Okay, so Hagerstown's population, guys, I promise we'll be able to finish up here. Just give me 1 more minute, okay? Hagerstown's population, okay, decays, or you can say decreases, by 1% each year. Okay, that is the crucial part right there. Your homework, I want you to do the back. Homework is the back. Homework is the back. Homework is the back. If you finished already, then you're good to go. Homework's the back. I'll take it. Thank you. Homework's the back. Oh, that is probably right. Hey, good luck.
Thank
You'll do
you.
fine.
Thank you.
The quick check, I can give you your quick check tomorrow. Okay, sure. Just because I gotta hold on to some of those people. It's just the back of the paper there, Brady. Braden, here's the homework paper right here. Thanks.